National Electrical Code Section 250.122b addresses equipment grounding conductor sizing when circuit conductors are increased in size to compensate for voltage drop. This section mandates that the equipment grounding conductor must be adjusted proportionately based on the circular mill area of the increased circuit conductors. To understand this requirement, let's delve into the principles behind it and how to apply it practically. Firstly, it's essential to understand why conductors are upsized. When electrical current flows through a conductor, there is an inherent voltage drop due to the conductor's resistance. The longer the conductor and the higher the current, the greater the voltage drop. Excessive voltage drop can cause equipment malfunction, inefficiency, and even damage. To mitigate voltage drop, engineers and electricians often increase the size of the circuit conductors, thereby reducing their resistance. Secondly, the equipment grounding conductor, or EG, plays a vital role in electrical safety. It provides a low impedance path for fault current to return to the source, facilitating the rapid operation of overcurrent protective devices like circuit breakers or fuses. This rapid clearing of faults minimizes the risk of electrical shock and fire. The size of the EGC is crucial for its effectiveness. If the EGC is too small, it may not be able to safely carry the fault current, potentially delaying the operation of the overcurrent protective device and increasing the risk of hazards. NEC Table 250.122 provides the minimum size requirements for equipment grounding conductors based on the rating of the overcurrent protective device. However, when circuit conductors are upsized for voltage drop, the standard EGC size may no longer be adequate. This is where Section 250.122b comes into play. The core principle of 250.122b is that the EGC must be able to handle the increased fault current that may result from the upsized circuit conductors. By proportionally increasing the size of the EGC based on the circular mill area of the circuit conductors, the code ensures that the grounding path remains effective and safe. Now let's break down the calculation process. The first step is to determine the required increase in the circuit conductor size. This is typically based on voltage drop calculations, which take into account the circuit length, current, and conductor material. For example, if a voltage drop calculation indicates that number 12 American wire gauge conductors are insufficient and need to be upsized to number 10 American wire gauge to maintain acceptable voltage levels, then the equipment grounding conductor must also be adjusted. The second step is to calculate the circular mill area of the original and upsized conductors. The circular mill is a unit of area commonly used to express the cross-sectional area of wires. You can find the circular mill area of different wire sizes in standard wire tables. For instance, number 12 American wire gauge copper conductor has a circular mill area of 6,530 circular mills, and a number 10 American wire gauge copper conductor has a circular mill area of 10,380 circular mills. The third step involves calculating the ratio of the upsized conductor's circular mill area to the original conductor's circular mill area. In our example, the ratio would be 10,380 circular mills divided by 6,530 circular mills, which equals approximately 1.59. The fourth step is to multiply the circular mill area of the initially sized equipment grounding conductor by the ratio calculated in the previous step. This will give you the required circular mill area of the upsized equipment grounding conductor. To illustrate this with an example, let's assume we have a 20 amp circuit using number 12 American wire gauge conductors, and NEC Table 250.122 calls for a number 12 American wire gauge equipment grounding conductor. As we determined earlier, the circuit conductors need to be increased to number 10 American wire gauge to compensate for voltage drop. The ratio of the circular mill areas is 1.59. Therefore, we multiply the circular mill area of the original number 12 American wire gauge equipment grounding conductor, which is 6,530 circular mills, by 1.59. This gives us a required circular mill area of approximately 10,380 circular mills for the upsized equipment grounding conductor. Fifth step is to select an equipment grounding conductor with a circular mill area that meets or exceeds the calculated value. Consulting a wire table, we find that number 10 American wire gauge conductor has a circular mill area of 10,380 circular mills. Therefore, we would need to use number 10 American wire gauge equipment grounding conductor in this case. Now, let's consider the specific scenario of running 120 volts 20 amp circuits and being asked to increase the wire size to number 6 American wire gauge on some circuits and number 8 American wire gauge on others to compensate for voltage drops, and the question of whether number 10 American wire gauge equipment grounding conductor is sufficient. According to NEC table 250.122 for a 20 amp circuit, a number 12 American wire gauge copper equipment grounding conductor is typically required. However, since the circuit conductors are being upsized, we need to apply section 250.122b to determine the correct equipment grounding conductor size. First, let's analyze the case where the circuit conductors are increased to number 6 American wire gauge. Number 6 American wire gauge copper conductor has a circular mill area of 26,240 circular mills, while number 12 American wire gauge has a circular mill area of 6,530 circular mills. The ratio of the circular mill areas is 26,240 circular mills divided by 6,530 circular mills, which equals approximately 4.2. Multiplying the circular mill area of the original number 12 American wire gauge equipment grounding conductor, which is 6,530 circular mills, by 4.2, we get a required circular mill area of approximately 26,251 circular mills for the upsized equipment grounding conductor. Looking at a wire table, we see the number 6 American wire gauge conductor has a circular mill area of 26,240 circular mills, which is very close to the calculated value. Therefore, in this case, a number 6 American wire gauge equipment grounding conductor would be required. Next, let's analyze the case where the circuit conductors are increased to number 8 American wire gauge. Number 8 American wire gauge copper conductor has a circular mill area of 16,510 circular mills, while number 12 American wire gauge has a circular mill area of 6,530 circular mills. The ratio of the circular mill areas is 16,510 circular mills divided by 6,530 circular mills, which equals approximately 2.53. Multiplying the circular mill area of the original number 12 American wire gauge equipment grounding conductor, which is 6,530 circular mills, by 2.53, we get a required circular mill area of approximately 16,521 circular mills for the upsized equipment grounding conductor. Consulting a wire table, we find that number 8 American wire gauge conductor has a circular mill area of 16,510 circular mills. Therefore, in this case, a number 8 American wire gauge equipment grounding conductor would be required. Based on these calculations, it is clear that a number 10 American wire gauge equipment grounding conductor would not be sufficient in either scenario. When the circuit conductors are increased to number 6 American wire gauge, a number 6 American wire gauge equipment grounding conductor is required. When the circuit conductors are increased to number 8 American wire gauge, a number 8 American wire gauge equipment grounding conductor is required. It's important to note that these calculations are based on copper conductors. If aluminum conductors are used, the circular mill areas and corresponding equipment grounding conductor sizes will be different. Always refer to the appropriate wire tables for the specific conductor material being used. In summary, when circuit conductors are upsized to compensate for voltage drop, NEC section 250.122b requires that the equipment grounding conductor also be increased proportionately based on the circular mill area. This ensures that the equipment grounding conductor remains effective in providing a low impedance path for fault current, thereby enhancing electrical safety. Always perform the necessary calculations and consult the relevant wire tables to determine the correct equipment grounding conductor size for each specific application. Remember, safety is paramount in electrical work, and adhering to code requirements is essential for protecting people and property from electrical hazards. Now let us consider other related and important factors to take into account when sizing equipment grounding conductors with voltage drop in mind. The first consideration is conduit fill. When upsizing circuit conductors and the equipment grounding conductor, ensure that the conduit fill requirements of Chapter 9 of the NEC are met. Adding larger conductors can quickly exceed the allowable fill percentage, requiring a larger conduit. Secondly, conductor ampacity should be considered. While upsizing conductors for voltage drop, verify that the selected conductor size has sufficient ampacity for the intended load. The ampacity of a conductor is its current carrying capacity, as specified in NEC Table 310.16 and other applicable tables. Thirdly, terminal compatibility must be observed. Ensure that the terminals on circuit breakers, equipment, and other devices are rated for the size of the conductors being used. Using conductors that are too large for the terminals can lead to improper connections and potential hazards. Fourthly, consider the effects of harmonics. In circuits with significant harmonic content, the neutral conductor may carry a substantial amount of current. In such cases, it may be necessary to increase the size of the neutral conductor and the equipment grounding conductor to accommodate the harmonic current. Fifthly, be aware of the minimum size requirement. Even after performing the proportional calculations, the equipment grounding conductor must not be smaller than the minimum size specified in NEC Table 250.122, based on the rating of the overcurrent protective device. Sixthly, consider the type of equipment grounding conductor. The equipment grounding conductor can be a wire, a metal raceway, or other approved means. The choice of equipment grounding conductor will affect the overall grounding impedance of the system. Seventhly, be aware of the requirements for long runs. For long circuit runs, the impedance of the equipment grounding conductor can become significant, potentially affecting its ability to effectively clear faults. In such cases, it may be necessary to use a larger equipment grounding conductor or to install additional grounding electrodes. Eighthly, consider the use of supplemental grounding. In some situations, it may be beneficial to supplement the equipment grounding conductor with additional grounding electrodes to improve the overall grounding system performance. Ninthly, review the local amendments. Local jurisdictions may have amendments to the NEC that affect the requirements for equipment grounding conductors. Always check with the local authority having jurisdiction to ensure compliance with all applicable codes and regulation. Tenthly, document your calculations. Keep a record of all calculations and decisions made regarding the sizing of equipment grounding conductors. This documentation will be helpful for future reference and for demonstrating compliance with code requirements. Applying these considerations, the correct equipment grounding conductor can be identified so that safety requirements are met. Always consult with a qualified electrical engineer or electrician to ensure that the electrical system is designed and installed in accordance with all applicable codes and standards.